Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to lecture 20 of this course on machine learning for earth system science. We are still in module 3, which is where we explore how machine learning can be used to discover new insights in earth system sciences. In the last lecture we had been discussing about identifying causal relations from time series. So today also we will continue the same topic. So the concepts which we are going to cover today are conditional independence based causality, PCMCI types of algorithms, and time series based downscaling with predictors. So like in the last lecture we are discussing about Granger causality, and its we also studied its use cases, say to identify the causes of rising global temperature and so on, where we tried to express the global time series of global temperature as a as a linear function of the time series of some other variables, including the CO2 concentration and so on. Now the Granger causality has certain drawbacks. It does not work well in the presence of confounders, autocorrelations in the time series, and contemporaneous relations. Confounders, as in, like if there, suppose there are multiple variables which we are focusing on, and that is in case of Granger variable, in Granger causality we are trying to express one variable as a linear function of the past values of the other. But if there, what if there are like another variable, there is a third variable which influences both the effect and the potential cause. In that case Granger causality may not make much sense. Then an alternative is to go for conditional independence based methods, which actually aim to identify these confounders and remove them with the help of the concept of conditional independence. So conditional independence between sets of variables can be estimated using statistical tests. So conditional independence is different from normal independence between two variables, in the sense that, like, let us say we have three variables x, y and z. So we know that we can call x and y as independent of each other if like the joint distribution of x and y can be factorized as the marginal distributions of x and y, that is p of x comma y is equal to px times py. But now if you consider the variable z, so like we can say that x and y are conditionally independent based on z if if the conditional joint distribution of x and y conditioned on z, it factorizes as the product of the conditional distribution of x on z and the conditional distribution of y on z, that is p of x comma y given z is equal to p of x given z times p of y given z. Now independence of x and y and conditional independence of x and y based on z are two different things, and one does not imply the other. So like if x and y are conditionally independent based on z, then it's not impossible that z may play some kind of a like a confounder between as far as the relation between x and y are concerned. Now it might happen that that is, if we ignore z and if we look for the relation between x and y, we may find some kind of a relation by Granger causality, and we may think that x is the cause and y is the effect. But in reality it might happen that actually both of them are conditionally independent based on z, that is, its z is a cause of x and z is also a cause of y. So these kinds of, if such a situation arises, then Granger causality is not able to detect them in any way. But if we have these the conditional independence based approaches, then we can like estimate this, or we can identify this situation and then identify z as a potential confounder. So, this accordingly we have the PC algorithm, which is known as like it is named named according to their inventors. PC algorithm identifies the cause of each variable with the confounders, and it can work well on time series data where the effects can be lagged as well as they are contemporaneous. So, Granger causality does not work at all on is not unable to identify contemporaneous relations at all. That is for the following reason, that when I am let us say that I am trying to express x t as a function of y t. Now, suppose I am able to do it, suppose it does turn out that x t is equal to like some a times y t plus other things. Now, even if that is the case, then we will never be sure whether to say that x t is the cause or y t is the cause, x t is the effect or y t is the effect. That is because if x t can be expressed as a linear function of y t, then y t can also be expressed as a linear function of x t. So, and we cannot understand any cause effect relation in that case. Apart from contemporaneous relations, like if x t could be expressed as in terms of past values of y t, then we could say that y is cause and x is effect, because the cause must precede the effect. But if in case of contemporaneous relations, we like there is no such constraint of related to time. So, we are not able to, even if we can find a contemporaneous relation, it does not help us to understand which is cause and which is effect. Now, this drawback of Granger causality is solved at least partially by the PC family of algorithms. So, here this kind of conditional independence of based causal inference, this can be used to infer causal relations between global climate indices. So, in different parts of the world, say for example, the ENSO index, which is related to the Pacific Ocean's temperature, or the ISMR, the Indian monsoon, that's another index, and there are various other indices in the related to various climatic variables in different parts of the world. Especially this is suitable for understanding the teleconnections and to eliminate the confounders. And this kind of approach can also be used to create causal networks of variables across the world, and these causal networks can also be constructed not only based on observations, but also on simulations, and then it is possible to compare the different causal networks also. The need for such comparison is that a simulation that does not reproduce the causal relations is unlikely to be very useful for the purpose of simulating different future scenarios. So, it is necessary to see if whenever there is a model which simulates the global climate or something like that, it is necessary to see whether it is able to, is it just simulating some kind of variables, or does it actually have the causal relations that are observed in the real world. Because if that is not there, then there is no point in using that model for future simulations. The future simulation we want to do, that is, if we are interested in asking questions like, if the global temperature rises so much, then what will be the effects of it, or if the carbon emission goes up like this, then what are going to be the effects of this. So, this can be a model can be able to answer this question meaningfully only if it is able to capture the causal relations well. So, it is very necessary to understand the causal structure or the causal relationships which any particular simulation model entails. So, one way to do it is through these kind of causal networks. Now, Granger causality, as we had said earlier, is unable to deal with this kind of phenomena. So, that is why we use the these conditional independence based approaches for this purpose of constructing these global climate networks global causal networks and comparing them. So, here is this paper appeared in 2012, quite some time back, about causal inference based on conditional independence. So, here they consider 4 major indices, as I was just talking about. So the causal discovery seeks to recover cause effect relationships from statistical data using graphical models. So remember graphical models we have already talked about is a graph where the different variables, each variable represents a random variable. One goal of this paper is to provide an accessible introduction to causal discovery methods for climate scientists with a focus on constraint based structural learning. By structure they mean the structure of the causal network. Second, in a detailed case study, constraint based structural learning is applied to derive hypothesis of causal relationships between 4 prominent modes of atmospheric low frequency variability in boreal winter. So these are the climate indices they are talking about. First of all, the WPO or West Pacific Oscillation, then East Pacific Oscillation or EPO, then Pacific North America per PNA pattern, and the North Atlantic Oscillation NAO. Now the relation between these variables, these are like roughly known to atmospheric scientists who have some intuition about the physics of the process, and they know which variable influences which other variable. The results are shown in the form of static and temporal independence graphs, also known as Bayesian networks. It is found that WPO and EPO are nearly indistinguishable from the cause effect perspective, as strong simultaneous coupling is identified between the two. In addition, changes in the state of either EPO or NPO may cause changes in the state of NAO or PNA correspondingly, approximately like 18 days later. In case of NAO and PNO, this lag period it becomes 3 to 6 days. These results are not only consistent with previous findings on dynamical processes connecting different low frequency modes, but also provide the basis for formulating new hypotheses regarding the time scale and temporal sequencing of dynamical processes responsible for these connections. Last, the authors propose to use structural learning for climate networks, which are currently based primarily on correlation analysis. While correlation based climate networks focus on similarity between nodes, independence graphs would provide an alternative viewpoint by focusing on information flow in the network. So this is the the PC algorithm which we talked about. This PC algorithm they have used for the structural learning, which is mentioned repeatedly in the abstract. So the PC algorithm, so this is the simplest or the most basic version of the PC algorithm. There are more sophisticated versions of it, as we will see later in this lecture. So the input here is a set of predictor variables x. Let us say there are small m number of such variables, and for each of them we have a time series of observations, and we have a target variable z. That is the z is the my observation which we for which I am trying to look for potential causes, and we also have a significance level for the causal independence test, which is called alpha. Like we know that for these tests or hypothesis testing, we need to have some level of significance based on which we can accept or reject the null hypothesis. So that is the alpha. So this is how the algorithm works. So the basic idea is that they consider different sets of variables, and that set S, that is of different sizes, and they take every single predictor x, and they see whether x is independent of the target variable z or not, given that particular S. And that for when they are testing for this independence, they use various statistical tests for conditional independence between different variables, and that those tests they require the significance level alpha. So and if they if x and z are found to be independent given z, then x is removed from the potential predictors of z, and so on. So, like finally what we are left, like step by step all these like differ each of the variables get removed or are retained based on the results of this kind of conditional independence test, and this conditional independence test must be done for different sets of variables of different sizes. And so, like ultimately what we are left with is a set or a subset of these very initial variables, the potential causes, and those that small subset which is left over after this algorithm, these are supposed to be the causes of the variable of the target variable z. And again these kind of things can, like if we are doing the lagged relation, then each of these variables x, the x1 x2 up to small xm, they must be considered at different lag values. So, in the study which they have done, this is the graphical model they have come up with as the output. So, like these each of these nodes stand for the different indices they mentioned. So, these arrows, these indicate like the cause effect relation, like for example this arrow, it indicates a like a that is, this is the cause and this is the effect, and each of these arrows, they are associated with some kind of a time period which means that the lag. So, like here it seems that EPO will be influencing NAO at a with a lag of about 18 days. Similarly, WPO has a weekly influences this PNA at a lag of 9 days. Similarly, there are these 0, they indicate contemporaneous relations, that is the cause effect relations take place simultaneously. And now causal independence based on conditional independence, in this case we need to calculate the causal relations at different lags for each pair of variables. Then there is the significance level alpha, this is an user tunable parameters, and so the relations should be strong enough to be detected by the test, and the study period should be representative of the full data set. So, now if the relation is weak, that is, it may, in that case depending on our alpha, it may not be detected by the test, that is the hypothesis may get rejected. Like that's again this is somewhat like the sparsity parameter which we talked about in the Granger causality. Just like for high values of sparsity, we have only a small number of variables, they pass the causality test, and hence we have a very sparse graph. So, similarly in this case also, depending on the significance level alpha, either very few or many of the potential predictors may pass this condition, may pass or fail these conditional independence tests. So, this significance level alpha, this largely determines how strong or how sparse this graph is going to be. And in some situations we may have some kind of domain knowledge, that is, we may already know by the according to our knowledge of physics, which climate scientists or other domain scientists may have, they can provide us some kind of clues that these two variables definitely have a relation, and this is a cause and this is an effect, or it might be negative also, that these two variables they do not have a relation. So, which they may have found out by other methods. So, if there such domain knowledge is available, it can be incorporated into the graphs either by forcefully inserting or by ruling out certain edges. So, this alpha, as I said, this largely depend or influences how sparse the graph is going to be. So, in this case, in the paper which we are discussing, if for very small values of alpha like this, then we have only 2 edges in the graph. So, this edge, as you can see, it's like it's an undirected edge, which means that we see that there is some kind of a relation between them, but we are unable to identify the relation, I mean, which is the cause and which is the effect. And then for slightly higher values of alpha, we may see that a few more edges may pass the test, and then as we go on increasing the value of alpha, we see that more and more edges are being inserted as the conditional because that is impacting the results of the conditional independence tests. now this same concept, this can be extended for more for other purposes also, and also for making them more robust to certain specific situations such as the contemporaneous and lagged relations. So this paper by Jacob Runge, who is one of the foremost scientists working on the domain of causality right now. So this paper, so what it does is it proposes an advanced version of the PC algorithm which we mentioned earlier. The paper introduces a novel conditional independence based method for linear and nonlinear lagged and contemporaneous causal discovery from observational time series in the causally sufficient case. Existing CI based methods such as the PC algorithm and also common methods from other frameworks like Granger causality suffer from low recall and partially inflated false positives for strong autocorrelation, which is an ubiquitous challenge in time series. Right. So, like we have already discussed in the previous lecture about the presence of autocorrelations, like in case autocorrelations are strong, like we may end up making some kind of mistakes in our estimation of the causal relations. The novel method, which they call as PCMCI plus, extends the PCMCI to include discovery of contemporaneous links. PCMCI plus improves the reliability of the conditional independence tests by optimizing the choice of conditioning sets and even benefits from autocorrelation. So, autocorrelation earlier was found to be detrimental to identifying causal relations, and they often resulted in mistakes, but here the claim is that this autocorrelation will actually be utilized to make a more efficient algorithm. The method of is order independent and consistent in the oracle case. A broad range of numerical experiments demonstrates that PCMCI plus has higher adjacency detection power and especially more contemporaneous orientation recall compared to other methods, while better controlling false positives. So, false positive, as you know, means that there is no relation, but or there is no causal relation, but your algorithm mistakenly identifies that there is a causal relation. And optimized conditioning sets also lead to much shorter runtimes than the PC algorithm. PCMCI plus can be of considerable use in many real world application scenarios where often time resolutions are too coarse to resolve time delays and strong autocorrelation is present. Like so, like if you see here in the PC algorithm, here like they are taking this set S of I mean the conditioning set, and for different set of these sets they are carrying out the conditional independence test. So, this step of course like is like this set S, it can be like any set of any size. So, like there is obviously a large space it covers. So, they are saying that in PCMCI algorithm they will navigate this smartly, and so that only a smaller number of this S variable needs to be chosen. So, this is the PCMCI plus algorithm, which is the sophisticated form of the PCMCI algorithm. So, as you can see, the input here is again the time series data set X of the different predictor variables n. Then there is the maximum time lag tau max, which is acceptable. Then there is a, just like we had the alpha, the significance threshold in the CI in the PC algorithm. In this case also we have the same alpha PC. We have apart from that we need a CI test, a conditional independence test involving like two variables x and y and a set and a conditioning set z, which returns a p value and a test statistic value. So, p value, like basically it means the probability of accepting the null hypothesis that x and y are independent given z. Basically this is how the algorithm works. I will not go into the details of the algorithm, but but once again the basic idea is that it takes us up this set S, the conditioning set, which is done in a smart way using the using the data structure, and like once that conditioning set is chosen, then we do this CI analysis. So note the presence of this t minus tau, that is they are actually calculating the lagged independence relations, that is instead of comparing xt and yt, they are considering xt minus tau and yt, like to take care of the lagged I mean the lagging effects. And so this as a result they get the value of this test statistic and also the p value. Now if that p value is greater than the alpha, that means that the condition they can accept the null hypothesis that there is that x and y are indeed independent given for this particular conditioning set S. So that basically means that x is not a predictor of y, so it can be removed for as I mean not x, I mean x at t minus tau, x at that particular lagged value, that is not a predictor of y, so we can remove it from the list of potential predictors, and we can turn on, and every time as we keep on iterating, we just keep on refining the this set, we keep on shrinking it, so that we have to do lesser searches over this conditioning set. So now we already talked about these causal networks for evaluating the climate model simulations. So causal networks for climate model evaluation and constant projections. So this is like another paper which appeared very recently. So global climate models are central tools for understanding past and future climate change. The assessment of model skill in turn can benefit from modern data science approaches. Here we apply causal discovery algorithms to sea level pressure data from a large set of climate model simulations, and as a proxy for observations, meteorological reanalysis. So reanalysis is basically the a combination of observations and simulations by different models. So this is done with the help of data assimilation. We have already talked about data assimilation in one of our earlier lectures. So when a climate or when any process model runs, and it is it is also calibrated with data at regular intervals of time, so that the simulations it produces are actually in sync with the real world measurements. That is called as reanalysis data. We demonstrate how the resulting causal networks or the fingerprints, as they can call it, they offer an objective pathway for process oriented model evaluation. Models with fingerprints closer to observations better reproduce important precipitation patterns with over highly populated areas such as the Indian subcontinent, Africa, East Asia, Europe and North America. We further identify expected model interdependencies due to shared development backgrounds. By that they mean that these models or the different process models which they are comparing, many of them actually have certain components or certain sub models in common, and as a result many of them may share certain biases and so on. Finally, our network metrics provide stronger relationships for constraining precipitation projections under climate change as compared to traditional evaluation metrics for storm track or precipitation itself. Such emergent relationships highlight the potential of causal networks to constrain long-standing uncertainties in climate change predictions. So, like let us say these are the observations which we have in of different Earth system variables in different parts of the Earth, and these are the simulated the Earth systems simulated by 4 different models. So, like for each of them we have measurements of the different variables. So, like which we can call as the time series. So, this is the let us say this is the observational time series of a particular variable, and these are the simulated time series. So, So first of all, they do some kind of like PCA algorithm to reduce the dimensionality and so on, and then they use this the PCMCI algorithm to build the network. So like these patches which you are seeing, each of these are numbered. So each of these patches actually are some kind of a index, and or like we can call these or we can understand these as variables, and so for each of these variables we have a time series. So so based on this they apply the PCMCI algorithm, and I construct the kind of causal network that they mentioned by adding a directed edge from one variable to another, provided they have some relation between provided they are not independent of each other. And so they finally come up with some kind of a fingerprint or a causal network like this, so where they have these kinds of time lags and so on. And once they have, so this is like the observation network which they might be getting. So these nodes, these are the different variables at certain periods of time, and then there are the we find that edges between different pairs of them, and each of these edges may have some lags also. And similarly for each of the simulations also we will find similar networks, and then we have to compare the different networks. Now there are different ways or different metrics of comparing two networks, like we can compare edge wise, or we can do component wise, like also we can compare the different properties of networks. So if you remember, in our earlier lecture on networks we had actually talked about some various connectivity and various other things. So all these structures can be the community structures of the different network, they can be identified and so on. So this paper they actually discuss a host of these network based metrics, in which they compare the observational network as well as the simulation network. And accordingly here they so these are the different climate models which they have compared. So these GFDL, CM3, EC Earth, etc., these are various models which participate in the CMIP project, the coupled model intercomparison project, where the models developed by various agencies in the world, they are compared, and then their relations with the actual observations here are plotted in this heat map. So these that is with the help of their corresponding network structure. So they have this F1 score. So F1 score, like basically it's related to the precision and recall, and they show here that the higher for the different models they calculate this F1 score, and the higher the score is, it indicates a greater degree of similarity with the of that simulations network with the observational network. So these are the references of the three different papers which we discussed today. The key points to be taken home from this lecture are that, first of all, the PC algorithm can be used to identify conditional independence relations, and then improvements to the PC algorithm work they work in presence of autocorrelation as well as the contemporaneous causality. And teleconnections can be identified using these methods, and the model simulations which may not preserve causal relations, they also can be identified by these methods. So that brings us to the end of this lecture. In the following lectures we will see some other applications of machine learning to find new knowledge in the domain of earth system science. So till then, goodbye.